This is AP Chemistry Screencast 2.6, Limiting and Excess Reactants. These sorts of situations happen in the world all the time. You are mixing things, or in nature things are being mixed, or in your body things are being mixed, but just in the amounts that happen to be present at the time, not the proper stoichiometric amounts. I would be surprised if an AP exam did not have a question that involved a limiting reactant situation. The basic idea, which you should be aware of from first year chemistry, is that if you know which reactant limits the process, which one you'll run out of first, that will be the determining factor in how much product you make. Let's go ahead and solve a given problem using the rather lengthy textbook method, and then I'll show you a shortcut method that you might want to apply for AP Chemistry. Whenever you do a shortcut, be aware that there's some limitations as well as some time savings, so we'll analyze both. All right, the question says we're burning 100 grams of butane. That's a pretty good cylinder of butane. And we only have 100 grams of oxygen. How many grams of carbon dioxide will it make? I wonder if that is enough oxygen, right? The textbook way to solve it is to see how much product both situations can make. 100 grams of butane, assuming excess oxygen, and the reverse, the lower number wins. Let's go ahead and do that rather quickly. It's a three-step process, gram-to-gram conversions. So we start with our 100 grams of butane. We recognize that 58 grams of butane is a mole. We recognize that each mole of carbon dioxide makes each mole of butane makes 4 moles of carbon dioxide, expressed there as 2 and 8, which is fine. And the mole of carbon dioxide weighs 44 grams, 12 for the carbon, 32 for the oxygen, telling us that we have enough butane, assuming excess oxygen, to make 303 grams of carbon dioxide. But we have 100 grams of oxygen. Let's assume that we have plenty of butane and see how much that can take us, how far that can take us. Well, 32 grams is a mole, 2 times 16, you get that from your periodic table. In this case, a mole of oxygen, 13 of them, is enough to make 8 moles of carbon dioxide. See the 13 and the 8? That's where they each came from. So you have a reducing factor there, which tells me that that's going to be a limiting factor almost certainly. And a mole of carbon dioxide still weighs 44 grams, so we only have enough oxygen to make 85 grams of carbon dioxide. That's going to be where the reaction stops because you've run out of oxygen and the butane can no longer burn. Now, if you want to take the chance, you could go ahead and solve this problem doing a little bit in your head. And here's how I would do it. You may make your own method. I just say to myself, well, let's see. Every 116 grams of butane, that's 2 times 58, is going to require 13 times 32. Let's see, what did I say, 116? 13 times 32, that's over 332 molecules. It's close to 400 grams, I should say, of oxygen. So we need way more oxygen than we do of carbon dioxide. We only have 100 of each. Clearly, oxygen is the limiting reactant, so you'll go ahead and skip this entire process here. You don't have to do this step at all. And in fact, you could say something like 100 grams of oxygen is how many moles of oxygen? I'd divide it by 32, and then I would simply multiply that by, let's see, oxygen to CO2, by 13 over 8. I'd say, oh, what a mess. I'm going to just go ahead and do it in the textbook way at this point and get my 85 grams of carbon dioxide and be done. And then I double check everything. You can make 85 grams of carbon dioxide. Oxygen limited this reaction big time. The excess must be the butane, but you might ask how much of the butane remains, and that is the kind of thing that I could imagine the AP people wanting you to know. The strategy can be simply, well, how much got consumed, right? And we can do that. We can say, given 100 grams of oxygen, how much butane does it require? That's a three-step process. So we go from grams of oxygen to grams of butane, right? We can do that. 32 grams of oxygen is a mole. Anytime we react a mole of oxygen, there it is. It requires less 8/13 as many molecules of, we're going to butane. Every 13 of these only will require 2 of those. See, so 13 moles of oxygen requires 2 moles of butane. Notice that you always have to keep track of where you're going, right? They're asking how much we're going from oxygen to butane. So we have to ignore carbon dioxide, we ignore water, things like that, and that's easy to mess up. Just make sure you're answering the question. So we're going from 2 moles of butane, which still, each mole weighs 58 grams. This reaction will consume, wherever it is, almost 28 grams of butane, meaning we have a little more than 72 grams of butane that remains. And that's how you do the last part of a limiting reactant type problem.